targets. So, trajectory of binding in molecule, protein, antigen, antibody, or other interaction is key to life and survival. Recently, thanks to the computational methods, the relevance of the molecular shape in drug discovery has been demonstrated. To be aware of that importance, here we show a brief list of some of the optimization algorithms that have been used during the latest years. But all these algorithms share that they only can compare two molecules at the same time. So, given a specific molecule which has the appropriate properties to produce a specific drug, this has to be compared one by one with the entire database. Therefore, the global elapsed time could be around 10,000 of seconds, depending on many factors. So, in view of this scenario, we wanted the following question. Is it possible to compare several molecules with the rest simultaneously? Currently, quantum computing is not accessible enough, and it doesn't seem especially interesting. But thinking that we can compare the bridge of Lisbon with hundreds of bridges that we have seen before, such as the Golden Gate, for example, why can't an artificial intelligence know when a molecule which is viewing at looks like others already seen? So, this is what we have built for our work. A neural network which receives a molecule as input, for example, this one which is used for producing ibuprofen, and in less than a second, or sorry, this is an optimized version, so it takes a little more time. So in less than a second, it can compute a similarity percentage of the rest of the molecules with itself. For example, clicking here in the output, clicking on them, we can see which are the most similar molecules, and we can compare with this display. Okay, so in this presentation, we are talking about how we have generated the data so as they can be processed by the neural network. Secondly, I'm talking about the structure of the neural network and the optimal results compared with other optimization algorithms. Lastly, I'm explaining a bit deeper the web application I showed some seconds ago. But we need to train our artificial brain, so we should follow a similar strategy than we did with this. Everybody here recognizes the remote doesn't matter its position because we projected all kinds of remotes in thousands of positions each onto our eyes during all of our lives. Why can't do that with drugs? It's easy. We can project we can project any of them using thousands of views so that we can easily recognize them. Oh, this is an aspirin. So we only need to create a set of points of view. Equally distributed is preferred, but is not critical, as in other expensive programs like Galileo, Mediaset, etc. Fortunately, Fibonacci spiral provides a good approximation using a very simple algorithm. This animation easily shows how can we generate thousands of views of any drug. We also found that a slow twist rate of the camera also provides better data sets. But generating datasets would be quite faster if we efficiently distribute computation. So in our work, we employed a task farm paradigm where each CPU picks a molecule and computes and generates their corresponding projection. And we also implemented a version of the code for GPU, where we distribute each axis of the Fibonacci sequence to every CUDA thread, thus obtaining spectacular timings, as we can see here, compared with the GPU, CPU. But how does our neural network compute the similarity? When an image is input to the neural network, the information is passed forward to obtain an array of probabilities of belonging to each class, or in this case, each molecule. All the elements of this array must sum 1 due to the applied activation function, and we have to apply other preprocessing functions to the input image. The forward pass of the information and the back propagating of the gradient can be performed in a GPU. It is worth mentioning that we are using convolutional neural networks as this is a visual recognition task. So we need to consider some key parameters. So first of all, we configure the input pipeline to take advantage of the parallelization capacity of the CPU and the GPU. We tune the batch size to keep reducing times and increasing the accuracy. Every pixel value was readjusted to make a more stable gradient. Although it is known that the number of layers significantly increase the accuracy, and we have access to many structures which won the mixed-net competition, they were too heavy for our web applications. So we had to make a further study of the structure. We needed to take into account the number of convolutional filters and insights. We found that larger filters could capture large atom groups like this aromatic ring, whereas smaller filters gave no relevant information. So, with all of this, we built our neural network that we call Monolith 2D, since it was trained from bidimensional images. And we also considered to input the scale of each projection just before the fully connected layers. We trained our neural network by back-propagating the cross entropy loss, and we updated the weights with the Alan optimizer. And later, we built our confusion matrix to measure the reliability of the result, where each element is the probability of an image created from the molecule I to be a projection of the molecule J. We consider that our classifier performs in a proper way when the molecule I is similar to the molecule J and vice versa, besides its capacity of finding the ground truth. With these two parameters, we found that the dataset with a twist rate of 1 rotation per 30 axis showed a better performance. We also considered that 512 projections were more than enough because we achieved a good symmetry of the matrix, but with a much lower computational effort. But can our neural network really find similarities between molecules? Let's compare our classifier with an acknowledged optimization algorithm, the farm, and let's check if at least they concur in some cases. So we observe 3 different behaviors from this comparison. On one side, we have some there were some cases where the output of the neural network was the same as the obtained by the farm. In the video, we can see more or less the original molecule upper left, whose text is in blue, and just below in orange we have the molecule which Optifarm outputs as the most similar molecule. And we can see that the similarity percentage is the highest. There, and on the other side, we have some cases where the neural network agrees with that the molecule given by Optifarm is quite similar, but it thinks that there are other molecules which are closer in shape. For example, here we can see that the molecule with the highest probability upper right, but the other one, the Optifarm one, has also a considerable percentage. And the last situation are those where the neural network discards Optifarm results. For example, here we can see that the Optifarm one has a 0% of similarity. But in view of this video, our neural network doesn't seem to be on the wrong way. So let's go back to our web application. So I'm going to the config panel this time. I will pick a molecule, for example, this one.
No.
Ah, okay, sorry. I will pick a molecule, for example, this one, and I will choose the number of projections, and this is make a request to the DrugFun database. It downloads the .mol file, which has a complete information of each molecule, and we generated new projections of these molecules. For example, I set it to 10 projections, and we can see them here, and if we compute them, we can go to the display and check that they, depending on the number of projections, the accuracy. So the higher the number of projections, the higher the accuracy, because it has more images to compare. So we can try to put in a similar position, and then we'll go. So this is how our application works. Okay, so to conclude, now, okay, we think that we have built a powerful tool that is complementary to other optimization algorithms. We found an efficient way to create very large data set from 3D coordinates. We also found that the predicting times of each molecule was much lower than the optimization algorithms, and we think that this is a starting point which opens many hopeful paths of research. Thank you so much. Sorry about the technical issues. So if you want to make any question, I will answer them.
Thank you very much for your presentation.
Thank you.
So, is there any question? No?
I have one.
Yeah.
Maybe I missed that part, but you take photo with the Fibonacci algorithm to the molecule. What is the size of those photos? Of the image? I mean, what is the size, the dimension of this?
Okay. 256 pixels each side.
Okay.
Yeah.
More question? No? I have another question.
Yeah.
I could see that you have a scale factor in your mirror network, okay? Could you explain a little bit more the meaning of this scale parameter?
Yeah, of course. For example, if we have a very small molecule, such as the fluorhydric molecule, it is a very small molecule, and if we use the same size as the larger molecules, it will be a dot on the images. So we need to use different scales and to tell the network that difference we input another parameter.
Uh-huh. Very clear.
Thank you.
Thank you very much.
Sorry about the
No problem.